The concepts presented in this video might evoke existential unease. Consider what exists between your eyes and the screen where you're viewing this video. The apparent answer is space. However, is this answer truly straightforward? If prompted to demonstrate this space, you would find it impossible because it's intangible. You can indicate objects within space, their connections and interactions, but not the space itself. You might gesture towards the empty air and label it as space. However, as a physical entity, space isn't directly observable. Regardless of our efforts, we cannot visually perceive or physically interact with it. One might argue that such contemplation serves as mental exercise rather than yielding tangible insights. Advanced studies in physics suggest that the conventional understanding of space may be fundamentally flawed, indicating a profound anomaly. Unbeknownst to many, the space between your eyes and the screen harbors a profound enigma. Scientists' quest to understand the underlying nature of space could forever change our view of the reality around us. Max Tegmark is a theoretical physicist and cosmologist. Space is intangible, but everything else, what you're seeing and hearing and feeling right now, we can observe perfectly well. And it feels so real. Today, however, we're going to talk about why recent scientific developments are calling into question everything that seems true to us in the first place. Everyone in string theory is convinced that space-time is doomed, and we don't know what to replace it with. David Gross, winner of the Nobel Prize in Physics. Maybe what we call space is not only intangible, but has no real existence. If space really doesn't exist, then neither does everything in it. Without space, objects lose coherence, for it is possible to imagine space without objects, but objects without space become nonsense, just a set of words. This is akin to trying to separate the canvas from the painting, but that the painted objects remain. I'm pretty sure that space and time are illusions. They are primitive concepts that will soon be replaced by something more sophisticated. Nathan Seiberg, string theorist. The huge problem is that all of physics originates literally from the study of how objects move in space, and space defines virtually every quantity that physics deals with. You take an object, and everything you can say about it within physics is ultimately related to space. Distance, size, shape, position, velocity, direction, even color. It's the length of a light wavelength, which is again a spatial category. I have no doubt that space-time has no future. Nicholas Giesen, eminent Swiss experimentalist in quantum physics. Only a few properties of matter, such as electric charge, have no known spatial explanation, but they also give themselves away by changing the direction of motion in space. Objects absolutely cannot exist without space. Many separate arguments, very strong individually, suggest that the very notion of space-time is not fundamental. Space-time is doomed. There is essentially no such thing as space-time in the fundamental formulations of the laws of physics. This is very frightening because physics is supposed to describe what happens in space and time. So if there is no space-time, it is unclear what physics is about then. Nima Arkani Hamed, theoretical physicist. There exists a book titled The Case Against Reality: How Evolution Hid the Truth from Our Eyes by cognitive psychologist Donald Hoffman, which, despite its worn cover and unassuming title, delves into astonishing revelation. Hoffman, a respected cognitive scientist, employs mathematical models and formulates testable hypotheses. His podcast appearance on the Lex Fridman channel garnered the highest viewership in the channel's history. Though Hoffman's ideas may appear audacious, they merit consideration. Additionally, spooky action at a distance by science journalist George Musser is recommended by esteemed physicist and Nobel laureate Frank Wilczek, renowned cosmologist Max Tegmark, and distinguished astrophysicist Mario Livio, making it a noteworthy read. Some things in this book directly echo what Hoffman writes. After reading this book, you will realize that Donald Hoffman's point of view appears to have validity.
Space-time is doomed. It's very, very clear. It couldn't be clearer. And my emotions rebel left and right. When I sit there and say, okay, I am not something in space and time, something inside of me says, you're crazy.
Indeed, the human body itself is a physical entity within space. Furthermore, even abstract concepts like our thoughts are essentially impulses, traversing through spatial trajectories. If the assertions of the esteemed individuals quoted are accurate, implying that space and objects lack true existence, then what does that make us? When we open our eyes and scan the space before us, intuition suggests that we're simply perceiving objective reality, akin to recording a video. However, neuroscience reveals a different reality. Each time we open our eyes, billions of neurons and trillions of synapses within our brain come into play. Approximately 1/3 of the cerebral cortex, representing a significant portion of our cognitive processing power, is engaged in the act of seeing. What does the brain compute when we look? Let's consider a creature that arguably comprehends visible space better than humans do, viewing us perhaps as mere moving dots on a plane. The herring gull. How do these seagulls perceive their surroundings? One might presume that since gulls primarily navigate by flight, vision must be their paramount perceptual tool, much like humans who derive nearly 90% of their environmental information through sight. Hence, it seems reasonable to assume that gulls and humans perceive reality similarly. However, the truth is quite different. We remain largely unaware of how the world appears to these birds. For example, you are now seeing some object on your screen that can be described as a long red rod with 3 white rings. But if you were a newly hatched herring gull chick, you would instead be seeing your very own mother on the screen. In the 1950s, biologist and Nobel laureate Nicholas Tinbergen conducted a study that completely disorients our intuition. In his book, The Herring Gull's World, Tinbergen meticulously details this study, demonstrating an unexpectedly engaging portrayal of seagulls. Essentially, Tinbergen's aim was to decipher how newly hatched chicks unfailingly identify their mother amidst various objects. After all, for a chick to get food, it has to peck at its mother's beak, after which she passes the partially digested food to it through her open mouth. Tinbergen created numerous replicas of gulls, ranging from lifelike to simplistic, including mock-ups of heads mounted on sticks. Remarkably, Tinbergen discovered that the chicks couldn't differentiate between a real mother gull and these replicas. Even when the replicas were as basic as a head on a stick, the chicks failed to notice any distinction. Tinbergen's experiments involved dozens, if not hundreds, of these mock-ups, shedding light on the remarkable perceptual abilities of these birds. Furthermore, the chicks failed to discern any difference, even when the mock-up was flat and consisted solely of a beak. In the realm of the hungry chick, distinctions are limited to basic shape and color. Details and volume are inconsequential. The presence of a red spot on the mother gull's beak likely influences this perception. Again, only very conventional shape and color. You'll say that the chicks are just almost blind for now. That's what Tinbergen thought at first. But tests showed that the chick's eyesight was perfectly normal. Ultimately, Tinbergen, drawing upon his accumulated experience and insight, crafted a long red rod with 3 white rings. Surprisingly, the chicks exhibited even greater eagerness to beg for food from this altered model than from the real mother. This series of experiments underscores how disparate physical objects can elicit identical internal experiences in living beings. Donald Hoffman says that there's really nothing surprising about this sort of thing, because evolution doesn't favor a true perception of the world. I hope you heard that well. Hoffman and his research team have conducted extensive simulations of evolutionary games, running hundreds of thousands of these simulations. In these mathematical models, various environments were generated and 3 types of organisms competed for resources within each environment. The first type perceived reality as it truly was. The second type perceived only a partial reality. And the third type perceived no reality at all, relying solely on basic adaptation mechanisms. The computer then calculated the evolution of the interactions between these 3 types of organisms in each environment. Now, consider this carefully. Which type of organism do you think ultimately prevailed in the competition for resources? In almost all tests, organisms that saw no reality but were tuned for adaptability wiped out all organisms that perceived reality. The bottom line is that evolution does not favor true or accurate perception. That perception of reality simply disappears. Donald Hoffman. You see, according to Hoffman, evolution by natural selection methodically eradicates any reliable perception of reality, because reliable perception is inefficient. That is, imagine that among the seagull chicks, one suddenly appears that sees objective reality. One would think that this would greatly increase his chances of survival. But in fact, while he's sorting out whether it's his mother, all the food will be eaten by the other chicks, who react instantly as soon as they see an oblong shape with a red element. An organism that sees objective reality is always less adaptable than an organism of the same complexity that sees the benefits of adaptability. Seeing objective reality will lead to extinction. Donald Hoffman. Evolution simplifies the complexity of our surroundings by guiding actions towards practical ends. Recognizing the red rod with 3 white stripes as a mother gull is beneficial in terms of adaptability. According to Hoffman, the simplifying mechanisms governing a gull's perception extend beyond just recognizing its mother to encompass all interactions with the outside world. Consider any object in your environment. The mechanisms shaping the perception of gulls are akin to those shaping your own perception. So tell me, are you sure of what you see? Naturally, you'd answer affirmatively. While gulls may lack this certainty, if I perceive a ball as a cube, I'll verify by touching it. We'll delve into this further later. In the meantime, we can make an example of how people, like seagulls that have just hatched into a white light, in turn can't realize that it's not actually white. The screen you're watching the video from only has blue, red, and green LEDs. When these colors blend, they create light that appears white to us, though it isn't truly white. In nature, genuine white light emanates from sunlight, which is fundamentally distinct from what we currently perceive. However, our perception doesn't discern this difference, as our ancestors weren't hindered in reproduction by this limitation. It's crucial to grasp another concept. According to Hoffman, every sense of any living organism evolved not to mirror objective reality, but solely to swiftly and efficiently respond to stimuli vital for survival. While conserving energy, this applies not only to vision, but to all sensory organs. Hoffman terms this the adaptation trumps truth theorem. He refers to it as a theorem because he provides a mathematical proof. Undoubtedly, studying the limitations of human perception, while being human, is exceedingly challenging. Nonetheless, why should we, with our advanced senses, doubt that we perceive reality accurately? Paradoxically, Hoffman's theorem suggests that as senses grow more complex, they don't gain but rather lose the ability to unveil truths about objective reality. Consider an eye with 10 photoreceptors, each of which has 2 states. The adaptability defeats. Truth theorem states the probability that this eye sees reality is at most 2 in 1,000 for 20 photoreceptors. The probability is 2 in 1,000,000. For 40 photoreceptors, the probability is 1 in 10 billion. For 80, 1 in 100 sextillion. There are 130 million photoreceptors in the human eye. The probability is practically 0. Donald Hoffman. But you read it and think it sounds questionable, to say the least. However, it's not a new concept. Nearly 200 years ago, in his seminal work Critique of Pure Reason, Immanuel Kant, a German philosopher, argued that the objects and phenomena we perceive do not necessarily correspond to reality. Consider an illustration. Our perception acts as a veil surrounding something. This something is what truly exists in reality. Kant refers to it as the thing in itself, which we cannot directly access. We cannot remove this veil because we are essentially part of it. Following this analogy, we're not merely passive observers of objects. Rather, we actively construct an experience of these objects within our consciousness, as if we were feeling them out or shaping them. At the same time, this experience does not reveal the true properties of these objects. Because in this crude analogy, under the cloth there may be a cube, there may be a box, or there may be a computer system unit. According to Kant, when you perceive an object, say, as an apple, it does not necessarily mean that the apple exists in the external world. Rather, something is present that causes the apple to be perceived, but its true nature remains inaccessible. The entity that causes us to feel the apple exists outside of space and time, because according to Kant, space and time are not inherent characteristics of the external world. Instead, they serve as a framework for organizing our experience. Simply put, space and time for us are not something we first experienced and then abstracted as an idea. They are something we have prior to any experience. Like, for example, the fear of the dark. Outlets are an experienced and abstracted idea. Indeed, fear of outlets is a learned behavior. whereas fear of the dark seems innate. In the analogy presented earlier, space and time are intrinsic properties of our perceptual framework. Now, you might wonder why we should consider the ideas of a long-deceased philosopher. Who could have predicted that these ideas would find support in scientific findings? Consider the Nobel Prize in Physics awarded in 2002 to 3 scientists, among others, for experiments that challenge the position of realism in physics. Realism posits that nature exists independently of the measurement process. You might have heard of experiments involving entangled particles, where measuring the state of one particle instantaneously affects the state of another, regardless of distance. Crucially, the observer has the freedom to choose the measurement angle, and by doing so, you directly affect the result. So you give the particle a framework within which it can operate, and it adjusts. The trick is that the second particle, even if it's on the other side of the universe, will instantly recognize the angle at which its companion was measured, and instantly take the opposite value. It's as if there was no distance between them. Now, many scientists believe that there was no instantaneous connection. It's as if particles are like a pair of gloves in a set. If you take one and see that it's right, then the second one will definitely be left. But the Nobel Prize was awarded, in particular, for experimental evidence of violations of Bell's inequalities. In other words, it suggests that if particles were gloves, none of them would be either right or left until they were measured. To summarize first, particles have no properties until they are measured. And secondly, when one particle is measured, the other particle recognizes it instantly. And physicists note that all this is more like magic than anything they've seen before. As a science popularizer and editor, I've had many conversations with scientists from different communities. Those who study everything from subatomic particles to black holes to the large-scale structure of the universe. And time after time, I've heard something like this. Well, it's weird, and I wouldn't believe it if I hadn't seen it myself, but it seems like the world just has to be non-local. George Musser. Einstein found the concept of quantum entanglement, which implies the non-locality of the world, so unsettling that he famously referred to it as spooky action at a distance. To comprehend the notion of non-locality and why it's considered eerie, let's consider the following. In our everyday experiences, we understand that to exert influence on an object, we must physically touch it. Objects typically only respond to their immediate surroundings. For an action at one point to affect another point, there must be something in the space between them that mediates that action. For instance, the operation of a remote-controlled toy helicopter isn't due to some mystical force, but rather operates through the transmission of radio waves. This concept is known as the principle of locality, which posits that each object in the universe occupies its own distinct place, separated from others by vast expanses of space. Indeed, during Newton's era, many people found his law of gravitation deeply unsettling, not because it implied that apples fall and planets orbit the sun due to mutual attraction, but because Newton proposed that this force acts instantaneously across distances. Simply raise a finger on the ground, and all distant planets throughout the universe would immediately respond, even if ever so slightly. However, this notion remains perplexing. Gravity seemingly bypasses the empty space between objects, with its influence leaping from the ground to the apple and from a finger to distant planets. The more you contemplate it, the more uncanny it appears. Einstein, however, assuaged these concerns with his theory of relativity, demonstrating that gravitational effects are constrained by the speed of light. Can you remember your reaction when you first learned that nothing could move faster than light?
No!
Many people are frustrated by the seemingly arbitrary speed limits imposed on our world, which inhibits the possibility of large-scale space travel. But the important thing is this: you wouldn't want to live in a world without this limitation. This huge star, bearing a complex name, stands out for its staggering speed, hurtling along at about 3 million kilometers per hour. At this speed, this star formation of considerable magnitude could cover the distance to the moon in less than 8 minutes. Scientists suggest that there are about 1,000 such stars, called hypervelocity stars, in our galaxy. The mechanisms that cause these space giants to reach such enormous speeds have prompted various theories. However, this hypervelocity star most likely had a companion, and their orbits intertwined, until the gravitational forces of the supermassive black hole at the center of our galaxy intervened, causing one of them to die. The second star had no choice but to rush into space with wild momentum. What is the significance of all this? Without speed limits, a variety of disturbing scenarios can unfold. For example, French mathematician Paul Painlevé described a scenario in which a star could leave a black hole at infinite velocity. In this case, a star accelerated to such limits from anywhere in the universe could instantly annihilate the solar system, leaving us no time to comprehend, detect, or even calculate such an event. It's actually worse than that. According to the theory of relativity, cause and effect relationships can be broken when the speed of light is exceeded. Now, the known laws of physics suggest that a killer star could have come to us from the future. Infinite speed is not an intuitive thing, and it erases the concept of space. As soon as you say the words infinite velocity, it's clear that there's something wrong here. Infinitely fast motion hardly has the right to be called motion. An object that is in motion is already at its destination. Therefore, how can it be said to be moving there? George Musser. Consider a scenario where a ball from a distant galaxy collides with a ball in your backyard and returns instantaneously, without consuming any time. This scenario is akin to one where one ball mysteriously influences the other, or where there exists no spatial separation between the two balls. Do you grasp why entangled particles raise concerns? For physicists, it's imperative to uphold the concept of space and the absence of such mystical occurrences in our universe. Consequently, they might entertain the existence of other phenomena just to rationalize this long-distance effect. Now you will learn everything, but just in case, hold on to your chair. The concept of superdeterminism posits that every action taken by experimenters in labs worldwide was predetermined since the inception of the universe. Thus, while an experimenter may feel they have the freedom to measure photons at various angles and locations, in reality, all their actions are predetermined to yield outcomes that appear coherent, even though there may be no actual coherence. For instance, the experimenter might experience distractions, like an itchy nose, or a phone call from their spouse to deter them from conducting experiments deemed undesirable by the universe. At first glance, this hypothesis may seem like a paranoid absurdity. However, it finds support from esteemed physicists like Nobel laureate Donald Hoffman, a key figure in the development of the Standard Model. He contends that maintaining locality is paramount for physicists. Consequently, even seemingly outlandish ideas must be considered to uphold this principle. Without locality, formulating the fundamental laws of physics would become exceedingly challenging, if not impossible. Hoffman says some new law of physics could presumably harmonize the properties of particles with the way people choose to measure them. What seems like a conspiracy today may be happening because of a conservation law that we don't know about yet. Donald Hoffman. Another, equally crazy way to keep things local is to suggest that particles can see the future, and that particles can be influenced by events that, from our point of view, should happen in the future. According to this hypothesis, the future should be able to influence the present in the same way that the past does. Particles could be born already having a memory of what will happen. Specifically, they may remember the settings of the polarizers they will later encounter and be ready to react accordingly. And if you've watched this clip, you're probably not likely to be very surprised by such a hypothesis. This idea has already been taken seriously. Physicists Richard Feynman and John Wheeler, who clearly need no introduction. That is, from the point of view of scientists, these options are incomparably better than the annihilation of space, and entangled particles are just one aspect of the problem. Imagine you turn on a light bulb. The atoms inside the filament start emitting photons. How do you visualize this process? You might imagine the initial photon flying out of the bulb like a bullet in a certain direction. However, according to quantum mechanics, the trajectory of the photon does not obey any known laws of physics. Instead, the photon emanating from your bulb propagates in all directions simultaneously, creating an expanding bubble in space. Only when it encounters an object does this bubble collapse, with a certain probability, collecting all of its energy in one place. Physicists call this the collapse of the wave function. The light you perceive from your lamp is due to many such bubbles bursting on the retina of your eyes. This phenomenon is not only characteristic of lamplight, it applies to all light sources, including distant stars and galaxies. If you haven't grasped the issue yet, consider this. One of the most distant objects, visible to the naked eye, is the Andromeda Galaxy, situated approximately 2.5 million light-years away from us. Now contemplate what occurs when you gaze at this galaxy. The bubbles of light that commenced their journey 2.5 million years ago have expanded to a diameter of 5 million light-years, only to collapse upon your eye's retina instantaneously. Remarkably, the sections of these bubbles separated by 5 million light-years abruptly halt their expansion upon reaching your eye, seemingly oblivious to the vast expanse of space between them. This perplexing phenomenon is known as the bubble paradox. Some might question, what are these photons? They're just tiny particles, yet quantum mechanics delves into the intricacies of the microcosm, revealing profound mysteries, even in seemingly insignificant elements. But photons are the most common particles in the universe, described by the Standard Model. And as far as people can tell today, quantum mechanics is not a theory of the microcosm, it's a theory of the world. The smallest particles make up all of existence. To give you some sense of the scale of the problem, Einstein, in an attempt to take a break from thinking about this behavior of light, you know what he did? He created the general theory of relativity. To quote George Musser, it's about the same as a vacation from peace negotiations in the Middle East, inventing a cure for cancer. To summarize, non-locality is this situation in which objects affect each other completely ignoring the space lying between them. I have always thought, and continue to think, that the discovery and confirmation of non-locality is the most astounding discovery of 20th century physics. Tim Maudlin, one of the world's leading philosophers of physics. Physicists are constantly discovering more and more mysterious and non-local phenomena that may at first seem disparate and unrelated. However, scientists say that these phenomena are interconnected at a deep level, even though they seem far removed from our everyday experience. Just as a few drops of water hint at the vastness of the ocean, or watching a falling apple leads to thoughts of black holes. So, rest assured, all the examples of non-locality are like puzzle pieces that will fit very seamlessly into the craziness we'll be talking about a little later. When looking at the night sky, it may appear unremarkable at first glance. However, this perception changes upon realizing that matter in the early universe could have been distributed in myriad ways, making it not just improbable, but virtually impossible for it to achieve uniform density and temperature at all points. Any two galaxies or two large clusters of gas at opposite ends of our sky, at the very edge of the observable part of the universe, are so far apart that light from the Big Bang has not yet had time to travel from one galaxy to the other. So you see, they can't even see each other. They couldn't exchange energy or matter in any way, and yet they're very similar. American physicist Charles Meisner said, "It is extremely difficult to explain why the sky is not speckled with spots. Observations have shown consistency in objects that have never had a physical opportunity to interact with each other." In 1970, Russian theorist Yakov Zeldovich ventured to propose that a form of quantum non-locality could elucidate the uniformity of space. This was a daring suggestion because suggesting a violation of locality implies that space fails to fulfill its fundamental functions. Moreover, if non-locality indeed exists in nature, it poses a significant challenge to science, as the cornerstone of the scientific method is to establish causal relationships and predict outcomes. However, how can one ascertain causality if objects can seemingly influence each other instantaneously and at any distance through magical means? Any challenge to locality inherently questions the nature of space itself, thereby casting doubt on theories grounded in spatial principles. This skepticism extends to virtually any theory we currently possess. Einstein recognized the potential flaws in the principle of locality, and by extension, our understanding of space. A few months before his death, Einstein pondered what the disappearance of space might mean for our understanding of the world. Then nothing would remain of my air castle, including the theory of gravitation, as indeed of all modern physics, Albert Einstein. Even Niels Bohr, who disagreed with Einstein in many other ways, called long-range gravity irrational and utterly incomprehensible. Meanwhile, physicists who study black holes believe that matter in these cosmic objects can jump from one place to another without traveling the distance between them. As Musa suggests, the main mystery lies not in the external aspects, but in the very heart of black holes, in particular in their singularities. Is this where you think the singularity is in a black hole? According to the general theory of relativity, matter inside a black hole reaches infinite density, resulting in an infinite distortion of space-time. The question of the location of the singularity implies the existence of space, and asking where the singularity is located implies the existence of space. So how can we ask where, if the space relative to which the position of the singularity is to be determined no longer exists? There is no here or there, or any fixed position relative to which the singularity can be defined. Paradox. And so the answer also sounds paradoxical. Inside a black hole, the singularity exists nowhere, and at the same time exists everywhere. It is a concept that defies ordinary understanding and is difficult to grasp. The topic of spatial anomalies is not limited to the phenomenon of black holes, but permeates various areas of physics, manifesting itself in quantum experiments, black hole paradoxes, and the cosmic structure of the universe. In all these examples, physics is entering the twilight zone. Distance can lose its meaning. The universe becomes unrecognizable. As said, although these types of non-locality appear in different contexts, they have a remarkable similarity that suggests physicists are groping different parts of the same elephant. What you will hear next will probably give you some serious psychological discomfort. Ernest Rutherford, the pioneering figure in nuclear physics and Nobel laureate, was the initial individual to ascertain via meticulous experimentation that atoms are overwhelmingly empty space, comprising 99% of their volume. Consequently, he recognized the profound emptiness inherent in the physical universe. Legend has it that he was so startled by the discovery that when he woke up the next morning while trying to get out of bed, he abruptly yanked his foot off the floorboard and crawled back under the covers because he was afraid of falling through the floor. We believe that there is a three-dimensional world that exists even when no one is looking at it, and that it contains real objects, like apples and misty waterfalls. Donald Hoffman. Black holes are eerie entities that arguably would be best left non-existent. If you haven't pondered them deeply, you might not grasp their unsettling nature. Countless perplexing theories revolve around them, particularly concerning the enigmatic singularity's elusive location within. What more can be said? But no, they continue to amaze. Anyway, Jacob Bekenstein and Stephen Hawking have calculated that black holes increase their size in a highly suspicious way that is atypical of the three-dimensional world. Imagine you have a box that holds one object. If you take another box with 2 times the length of its edges, its surface area will be 4 times larger, and its volume will increase 8 times. In other words, if you can fit one object into the first box, you could fit 8 of the same object into the second box. This principle, known as the square-cube law, was demonstrated by Galileo 400 years ago. It's how geometry operates in our three-dimensional world. Can you imagine it functioning differently? Yet, this law doesn't hold true for black holes. Ordinarily, you might expect a black hole to behave like the box scenario. Doubling the radius of a black hole would theoretically increase the area of its sphere by 4 times, and the volume, hence capacity, by 8 times. However, this isn't the case. When a black hole's radius doubles, the area of its sphere does increase, as anticipated, by 4 times. But its volume increases not by a factor of 8, as expected, but also by a factor of 4. So it's as if in the example with the second box, we would visually have space for 8 items, but could only fit 4. Despite all the apparent volume of space inside, something would prevent you from putting the 5th item in there. This is only possible in one case. In fact, increasing the width and length of the hole increases its capacity, but the extra height does nothing. It's as if this dimension is illusory. George Musser. Hence, the perplexing paradox. Black holes, although appearing three-dimensional, behave akin to two-dimensional voids. How can something ostensibly three-dimensional behave in such a manner? A two-dimensional object in three-dimensional space, and therein lies the crux of the issue. Black holes aren't mere abstract concepts. They possess the capacity to engulf entire solar systems, albeit they reside far from us. One might assume that their peculiar behavior wouldn't impact us directly, but this story has far-reaching implications. Hawking and Bekenstein swiftly recognized that this principle extends beyond black holes to encompass the entirety of space. If this notion seems baffling, Donald Hoffman elucidates with a straightforward analogy. The maximum amount of information that 6 spheres can contain will be greater than the maximum amount of information that one large sphere could contain, in which those 6 could fit. That is, volume literally plays no role. Only the surface area is important. In our everyday world, far from black holes, however, objects also look like 3-dimensional objects, but behave like 2-dimensional objects. I want you to understand very well what is meant by this. If you try to fit exactly as many things as a particular region of space visually offers, that region of space will collapse into a black hole, which will already take up as much space as it needs. It's called the holographic principle. Physicists Leonard Susskind and Gerard Hooft have been studying it. Susskind says, "Here is the conclusion that Hooft and I came to. The 3-dimensional world of our ordinary experience, the universe filled with galaxies, stars, planets, houses, rocks, and people, is a hologram, an image of reality encoded on a distant 2-dimensional surface. This new law of physics, called the holographic principle, states that everything inside some region of space can be described by means of bits of information located at its boundary. Despite ongoing debates among scientists regarding the universe possibly being a holographic projection, the nature of the projector, and the characteristics of a fundamental 2-dimensional surface, this principle has gained widespread acceptance in theoretical physics. Consider the vast expanse of space around us. It seems capable of accommodating an abundance of matter. Yet in reality, it contains far less than it could potentially hold. Attempting to fill this space yields a peculiar realization. There isn't more space in our 3-dimensional universe than there would be if it were 2-dimensional. This prompts a profound question. Does space truly exist as we perceive it? Or is it a form of visual illusion? Juan Maldacena, a proponent of string theory, introduced the ADS-CFT concept, bolstered by the holographic principle. According to this notion, seemingly distant regions may actually be superimposed upon one another. And one of the spatial dimensions we occupy is actually not a spatial dimension, but an energy, and what appears to be a distance in space is in reality a difference in energy. If you haven't figured it out yet, University of Maryland professor and theoretical physicist Raman Sundram explains it this way. It's the same as creating a sense of space on a flat canvas. You're just depicting 2 distant objects at different scales. Humans are much smaller than buildings, but because of the distance in space, they are depicted almost identical. Something similar happens in the ADS-CFT scenario. The universe looks 3-dimensional, but in reality it may be a 2-dimensional canvas. What we perceive as distance along the 3rd dimension is ultimately a difference in scale. The distant object is actually right next to you. It looks small because it is actually small. You cannot touch it, not because it is distant, but because it is too small to feel. When objects increase or decrease in size, we perceive it as movement toward or away from us. Objects of different sizes are not strictly independent. They interact with objects of comparable size, and the results of this can be transmitted from one scale to another. George Musser, at the most fundamental level, distance may not matter. People may be separated by an ocean of space, but actually be near each other in some deeper sense. Apparently, however, our existence requires the appearance of the concept of distance. And so, evolution has created this illusion for us. For Einstein, the need to touch in order to make an impact was something on the level of common sense. On the other hand, he realized that anything seemingly common sense needs proof. And now, we realize how exceptional and fragile the fact of distance is in reality. The point is that the space we observe may be the product of some underlying structure. As we walk through a room, we are not sliding passively in an already existing space. Something is going on all the time. Some mechanism is at work, some kind of spinning wheels in the mysterious depths of nature that create the impression of being here and being there. When you reach out your hand for a pencil, but you cannot reach it, something prevents you creating something perceived as distance, And it's worth asking what that mechanism is as we get to the cutting edge of modern physics. George Musser. Consider a scenario where you're moving steadily through outer space, without any external reference points to gauge your motion. How would you even perceive that you're in motion? You wouldn't. There's no tangible sensation of movement. In this context, the experimentally validated effect of Einstein's theory of relativity takes on a new dimension when you expend energy to accelerate. Space, effectively, contracts along your trajectory. Moreover, our ability to accurately assess the properties of objects in space is often flawed. For example, you'd be willing to swear right now that the cars on the screen aren't the same size at all. This is the Ponzo illusion, in which the size of objects feels different, even though they are the same size. Or the moon illusion. This is when the moon above the horizon appears several times larger than when it is high in the sky, although its angular size is always the same. People still haven't found a clear explanation for this phenomenon of human perception. Again, perhaps all of this will seem even a little less crazy if we remember that no human in history has ever seen anything in 3 dimensions. Many people think we see the world in 3 dimensions, but in fact, we only see a 2-dimensional projection. The sense of volume, on the other hand, is created by our brain. As Richard Feynman said, what can be said about the interior of a brick? No one has ever seen the inside of a brick. Every time you break a brick, you only see the surface. The way a brick is organized from the inside is just a simple theory to help us understand things better. This is why experiencing an image on a flat screen is almost as good as experiencing the real world. According to Donald Hoffman, our senses are not searching for truth. They're looking for adaptability, and so they respond only to specific patterns. And even if they understand this, they can be easily confused by very primitive technology. This picture demonstrates exactly how our brains pump objects up in volume, reading messages related to adaptability. When we look at a car, we do not reconstruct its true 3-dimensional shape on our internal screen. The language of 3-dimensional shapes is the language our brain developed for it by evolution. In reality, however, no 3-dimensional things exist. And although we are genetically similar to other species, they may have a completely different concept of space and objects. For example, David Marr, the man who revolutionized the study of human vision in his book, Vision, writes, "Visual systems, such as that of the fly, are not very sophisticated because they collect very little objective information about the external world. The relevant information is generally extremely subjective. It is extremely unlikely, in particular, that the fly has any explicitly given representation of the image of the world around it. It does not have, say, a correct idea of what a surface is. It is very difficult to understand how a fly can have no correct notion of what a surface is, or of the external world in general. It performs such pirouettes in space, instantly evading the surface of the fly swatter. The simplest signals associated with adaptability are sufficient for this. One reason for this simplicity of the system must be the fact that it is this data that provides the fly with the information it needs to survive." David Marr. When you examine your computer desktop through a magnifying glass, you perceive millions of pixels, the smallest discernible units of the screen, all appearing flat. However, stepping back reveals breathtaking 3-dimensional worlds with intricately detailed objects. For example, if you play games or watch movies, and yet the information that makes it all add up completely. The same is true when you shift your gaze from the monitor to the world around you. Information is 2-dimensional in both the first and second case. Both there and here calculate patterns of adaptability. This parallels the experience of a gull chick, which, upon seeing a red rod with 3 stripes, perceives no distinction between it and its actual mother. According to Hoffman, just as evolution has deemed only very conventional shape and color a successful solution for the vision of a hungry seagull chick, space-time and objects have been a successful option for human vision. We see objects in 3 dimensions, not because we are recreating objective reality, but because that is the format of the compression algorithm that evolution has built into us. You will say that this sounds implausible, not because we see the world flat or not flat, but because we literally feel that we are in a 3-dimensional world. We see an apple, we see that it is three-dimensional. We take it in our hand and feel that it is indeed three-dimensional. It can't be a mere coincidence that different senses are telling us the same thing. But ask yourself, how do you know what you know? And what makes you think you know it? What makes you think that touch gives us reason to believe that an apple has what we call volume? In 1688, the natural philosopher William Molyneux posed the question in a letter to John Locke. Suppose a man is born blind, grows up, and is taught to distinguish by touch a cube and a sphere of the same metal and of about the same size, so that he can tell, by touching one and the other object, which is a cube and which is a sphere. Suppose further that the cube and the sphere are placed on a table, and the blind man is given the power of seeing. It is asked, can he now, by means of his sight, before he touches them, distinguish them, and tell which is the sphere and which the cube? Both philosophers agreed that it could not. In 1709, in an essay towards a new theory of vision, George Berkeley also concluded that there is no connection between the world of touch and the world of sight, that the connection between the two can only be established by experience. And what is wonderful about the modern world is that nowadays we can experimentally verify the answer to this question. Between 2007 and 2010, 5 patients were surgically cured of congenital cataracts under the direction of Indian scientist Pawan Sinha. The treatment quickly brought the patients from complete congenital blindness to full vision, and each was given an elaborate test within the next 48 hours. And surprise, they couldn't make a connection between objects perceived by 2 different senses. The correlation was barely better than if the subjects had just guessed. They had no innate ability to transfer their tactile knowledge of shape to the visual domain. The performance improved only over time, and not by 100%. It's very difficult for us ordinary people to understand, because we can see with our hands, in a sense. Just by closing our eyes and feeling something, we can quite easily visualize what the spatial shape of that object is. So how can sight and touch be unrelated? It's like this. We can think that an apple is spherical in both sight and touch, but the information from the different senses is not connected. It's experience that makes it connected. So, do you think a person who has just acquired touch with their eyes closed would be able to tell by touch whether they are touching the flat side of a cube or the three-dimensional surface of a sphere? Einstein never stopped pondering the meaning of quantum theory. We often discussed his thoughts on objective reality. I remember once on a walk, Einstein suddenly stopped, turned to me, and asked me if I really believed that the moon exists only when I look at it. Abraham Pais, theoretical physicist, historian of science. Anti-realism assumes that the act of measurement plays a fundamental role and actively helps to create reality. This point of view was held, for example, by Niels Bohr and Werner Heisenberg, the founding fathers of quantum mechanics. The former one said, "Nothing exists until it is measured," and the latter said, "What we observe is not nature as such, but nature subjected to our method of questioning." This is the same point of view held by Anton Zeilinger. He is one of the 3 scientists who won the very same Nobel Prize in 2002 for experiments that essentially dealt a serious blow to realism. Francis Crick, one of the discoverers of the structure of DNA, wrote in correspondence with Donald Hoffman, "It seemed to me, following Kant, that we must distinguish between the thing in itself, which in principle is not cognizable, and the representation of the thing that our brain creates. In the end, Donald Hoffman himself believes that the universe, as we know it, really doesn't exist as long as no one is looking at it. But it is not that the observer literally creates this universe, or that he can influence the world by force, thought, and other such things, which science treats with a fair amount of skepticism. Think of the 2-slit experiment. What happens when we put photons through 2 slits? And if photons behave like bullets, then on the screen behind the 2-slit partition, we'd get a 2-band distribution. But since photons, until they are caught, propagate in all possible directions and behave like probability waves, we get a normal probability distribution on the screen. Most photons are registered in the middle, since their registration is most probable there, and a minority on the sides, since it is least probable there. However, if we put detectors near both slits to see which slit the photon passed through, the wave function will collapse, not on the screen at the back, but near the first or second slit, since the measurement happened there, and the already measured photons on the back screen will show a 2-band distribution. But if you set up only one detector near only one of the slits, the photon, even if not caught at that slit, will still behave as if it were caught at the neighboring one. And the pattern on the rear screen will be the same two-band pattern as in the situation with two detectors. That is, as we see for the collapse of the wave function, it is enough, not just a measurement, but even just the principal possibility to get information about the location of a particle. Because similar tricks in two-slit experiments demonstrate not only massless photons. In September 2015, a world record was set at the University of Vienna under the direction of Marcus Arndt. During this experiment, it was possible to observe wave quantum properties in a huge molecule of 2,000 atoms in size. So quantum weirdness is not limited to the subatomic level. It extends to all matter. And one of the most influential theoretical physicists of the 20th century, John Wheeler, said, "Nothing that exists can hope to be considered fundamental unless it translates the entire physics of the continuum into the language of bits." He insisted that space-time and its objects are non-fundamental. Instead, he proposed the it-from-bit principle. The principle is that it is information, not matter, that is fundamental. Matter, on the other hand, arises from bits of information. Hoffman picks up on this idea and says that we don't know what the true universe is, but our perceptual fabric overlaid on that universe is a code for accommodation. He calls this the interface theory of perception, and it's about time we put into simple words how Donald Hoffman sees the world. Suppose you write a letter on your computer in which you give the object of your affections arguments about why it is worth going on a date with you. Then you save it to your desktop before sending it. Here it is. The file icon is blue rectangular and located in the center of the desktop. But does that mean the file itself is blue, rectangular, and in the center of your computer? Of course it doesn't. The color of the icon is not the true color of the file. The shape and location of the icon are not its true shape and location. In fact, a file has no color or shape. A file is stored in a computer as bits of information, and the location of those bits has nothing to do with the location of the file's icon on the desktop. And it's not that the blue icon misrepresents the true nature of the file. It has no purpose at all to represent that true nature. On the contrary, its purpose is to hide that very nature and spare the user the tedious details of transistors, voltages, magnetic fields, logic circuits, binary codes, and gigabits of software. If instead of manipulating a file icon on your desktop, you had to manipulate bits, transistors, or electricity while you were trying to send your email, the object of your affection would have long since had children with someone else with a more modern computer. Computer interfaces have evolved just enough to hide all the internal complexity, all the truth that would serve as an obstacle to the task at hand. Can the icons and pixels of your desktop tell you anything about the internal hardware of your computer? They can't, and they shouldn't. The interface helps you create emails, edit photos, or search the web, and it also obscures how it actually happens. Our senses do the same thing. Get to know each other. Everything you see and feel is the Homo sapiens user interface. Space-time is our desktop, and physical objects like spoons and stars are the icons of the interface. When you ask if the moon really exists, whether I can see its true color, size, shape, and location is like asking if the brush icon in Paint exists before I select it as my working tool, and whether that icon reflects the true color, size, shape, and position of the paintbrush inside my computer. Interface theory of perception suggests that our perception of the moon and other objects was formed not to reflect objective reality, but to detect the only thing that matters to evolution, a message related to adaptability. One might ask, if the scary big bear is just an icon, why don't I play with it? See, evolution has not formed an icon of ionizing radiation in our interface. We don't observe or feel the millions of muons damaging our bodies every day. It doesn't matter to evolution, but because it didn't prevent us from having time to grow up and have children. In pre-scientific times, no muons for humans simply did not exist. However, when you see a radiation danger sign, you take it extremely seriously, even though the radiation sign has nothing to do with radiation itself. You don't climb into a contaminated area. You don't grab the snake icon in your interface for the same reason that on a submarine you would take seriously a flashing green dot being carried toward the center of the screen. Torpedoes are obviously not green flashing dots, though. Evolution has shaped our senses to keep us alive. Therefore, it's best to take icons seriously. Seriously doesn't mean literally, however. I see a rattlesnake crawling towards me. I should take it seriously. But it does not follow from this that there is something brown, sleek, and sharp-toothed when no one is looking. Snakes are simply icons on our interface that drive adaptive behaviors like flight. Something continues to exist when I avert my eyes. But whatever it is, it's not a spoon or any object in space-time. Donald Hoffman. Our brain is not telling us that we are now perceiving electromagnetic waves that repeat themselves 450 trillion times a second. It's just telling us that we're seeing red. And according to Hoffman, something similar might be the perception of distance. What we perceive as space is an encoding of the energy expenditure to get resources. So, for example, if it takes 1 calorie to get an apple, it is perceived to be 10 meters removed in space. A predator, for example, might be the farther away the more calories it has to expend to get to me. Recent experiments support this idea. For example, Dennis Profit and colleagues found that people given a drink containing glucose give lower approximate distance estimates than those given drinks with an artificial sweetener, containing no carbohydrates. More exercise people give smaller approximate distance estimates than less exercised people. This suggests that our perception of distance does not depend simply on energy expenditure, but rather on the ratio of energy expenditure to energy available to us. Donald Hoffman. One might ask, well, what about the cameras we have created? Why do they see what we see? Or here's another historian and popularizer of science. Michael Shermer writes in Scientific American that the interface theory of perception deserves serious consideration and testing. But he has his doubts. Finally, why present this problem as an either-or choice between adaptation and truth? Adaptations depend heavily on a fairly accurate model of reality. The fact that science is moving towards, say, eradicating disease and landing spacecraft on Mars must mean that our perception of reality is getting closer to the truth. Michael Shermer to such an objection, and Donald Hoffman responds that it is true that, thanks to science and technology, we are becoming more and more adept at managing our world. However, this is roughly the same as players of Minecraft becoming more and more skillful in controlling its worlds. In Minecraft, for example, you can make a camera out of the simplest of blocks to capture the environment of the world of Minecraft, but that camera can't take pictures of the game's code. Similarly, by manipulating interface icons, you can make a computer to play Minecraft on while you play Minecraft. To a newcomer, an expert in the game will seem like a wizard, but that expert does so based on knowledge of the interface, not the truth. He may not understand anything about the complex algorithms behind the icons. All in all, if Hoffman turns out to be right, it's somehow uncomfortable to think that the world we know doesn't exist. And from Hoffman's point of view, many problems of existing physics and not only, and seemingly unsolvable, for example, difficulties with the unification of the theory of gravity and quantum mechanics, or the strange division of nature into living and non-living, they come from the fact that although science demonstrates that the icons on our desktops are not reality. For example, it turns out that there are atoms and subatomic particles that we do not perceive directly. However, we don't realize that when we take out a magnifying glass, look at the desktop and see pixels. We don't actually see the workings of transistors, electricity, and software code. Atoms and subatomic particles are invisible without special equipment. They are in space and time, and thus they are still at our interface, and thus cannot be the foundation of the universe. This mistake is understandable and even forgivable. Our nature limits not only how we see, but also how we think. Going beyond the limits, or even realizing that it is possible to do so, is not easy. But then why does Hoffman think his theory has a right to exist? Isn't she destroying herself by saying that we cannot go beyond our basic limitations? From Donald Hoffman's point of view, we actually can with the help of math. He believes that math may be fundamental in nature and capable of nudging us in the direction of truth. So, the main question. Obviously, following Hoffman's reasoning, our bodies are like interface icons, hiding a complex, unknowable reality. We don't know our real actions. We only know how we see our body icons interacting with other icons in our interface. If our bodies, like everything else, do not exist in objective reality, then what are we? The hard problem of consciousness is the problem of explaining how any physical system is capable of generating subjective experience. And from Donald Hoffman's perspective, the hard problem of consciousness is because consciousness is just a manifestation of a fundamental level of reality. Consciousness does not fit into the natural scientific world, because the world we study is our interface, and consciousness is not part of it. We study the human brain and try to figure out how the neurons in it, which are part of the physical world, produce something we call subjective experience. This is the so-called mind-body problem. I love the sun, and I don't want to part with my neurons. But I don't believe the sun existed before there were beings observing it, or that my neurons exist beyond observation. Stars and neurons are just icons on the space-time desktop of my perceptual interface. And just as my computer icon on the desktop can't give any insight into binary code, transistors, or electricity, in the same way neurons can't tell us much about consciousness. In fact, Hoffman has his own theory of consciousness called conscious realism. According to Hoffman, our consciousness, is a manifestation of the true mathematical nature of reality, the foundation of being. And if you think that everything said in the video is bold, I recommend you to read about this theory in his book. There it is, given a whole chapter. However, no matter how fantastic it may seem, Hoffman insists that it is not just a metaphysical concept, but that it is open to critical methods of scientific inquiry and can be experimentally tested. Thank you all very much for watching. Don't forget to share your opinions in the comments.